Okay, I'm sorry if anybody came here to, I've still got the wrong title up there. I put the wrong abstract in conference notes. This is actually going to be an update on my last talk, which was indeed about global analyses across a large code base. So what I'm going to be talking about largely today is the things I've been busy with in Clang plugins since the last time I was here. To give you some context, I largely write Clang plugins for LibreOffice, and that means that I build little pieces of code that plug into the Clang compiler and make use of the Clang AST APIs, and they enable us to implement various verification checks and to do some large-scale rewriting across our code base. So that these plugins have in the past enabled us to clean up things like the fact that we started our life with about 7 different string classes, and we've done pretty well. We're down to about 3 or 4, and it enabled us to clean up all sorts of little bits and pieces along the way, and it's enabled us to move to more modern usage of C++. My current status, some people will be happy to hear that I have in fact run out of ideas. My pipeline is rather empty, which means that there's not a lot of large-scale changes coming down my pipeline. The flatten plugin, which is there to reduce the indentation largely of code by reorganizing methods so that they do early exits, still has a fair number of stuff coming, but I don't have any new plugins coming. I track Clang upstream on a fairly regular basis. Occasionally the plugins need tweaking in order to accommodate mild changes in Clang. Clang's actually become really stable, and plugin APIs are actually really nice to use. They're pretty reliable these days. Occasionally I still run into issues with source locations being slightly out, ranges of source being a little bit iffy, but 95% of the Clang stuff these days, if something goes wrong, it's typically my fault. Okay, Unique Pitta is a plugin I've just largely finished pushing changes for. The point of Unique Pitta was to find places in our code base where we could productively use the standard unique pointer, smart pointer class. The point of using Unique Pitta is that it makes obvious something that is otherwise just implicit in your code. The fact that a given class or a given variable is the exclusive owner of another object. So my plugin started out using my favorite onion peeling strategy. Onion peeling means I look for very simple approaches and then I run the plugin across the entire code base. So I look for very specific patterns. So my plugin started out looking for patterns that look pretty much like that, where a class clearly is deleting a member field that it owns itself in its destructor. And I ran that across our entire code base of 10 million lines, looked for stuff, fixed it, and then I extended the pattern matching. And I've been gradually making the pattern matching more extensive. I've looked for more different patterns of owning and deleting pointers. And as I've kind of cleared out one set of changes in our code base, I've then made the pattern matching a little bit more flexible. I've got to the stage now where the pattern matching, in fact, is so flexible that it points up a lot of false positives, which means my plugin now has an awful lot of manual exclusions. But I consider that a worthwhile trade-off. I don't aim to make these plugins completely robust. They're not meant to be absolutely perfect plugins. That is just, in my opinion, largely a fool's errand. C++ just has vastly too many corner cases. If you want to make a plugin like this that's looking for issues completely robust, you will find yourself on a hiding to nothing, exploring all kinds of weird sub-parts of the C++ AST and macros and all sorts of other weird stuff. So I don't aim to do that. I just aim to get stuff that's useful for LibreOffice. That being said, these plugins are there, the source code's there. If anyone wants to try and extend them or upstream them or do something else with them, you're welcome to. I'm always happy to give assistance. But I have deliberately not tried to upstream these to LLVM because I know that they will inevitably come back to me and say, but what if, and what if, and what if? And they're right. It generates false positives. But we're happy with that, so we just keep trucking. Method cycles is a plugin that I fairly recently wrote, and I'm very proud of this one. It took me a long time to get to the point in time where I understood the Clang AST and I understood C++ well enough to be able to write it. What it does is it constructs a graph over our entire code base of method calls. So basically I have a map of pairs from source method to destination method, or actually from source function to destination function. And I remap it, I massage it slightly, so if you call a virtual method, it walks up the hierarchy to potentially multiple pairs and tags all of those with calls, and then we generate an entire graph. This takes 2 or 3 times longer than my normal runs do. It generates 40 odd gigabytes worth of log file data, and then takes roughly half an hour of processing with a Python script to spit out results. It only found about 7 things, because I have other plugins that look for unused code as well. But it found 7 things that my unused code plugin was unable to find, because they were cycles. The methods were calling each other in a nice little loop, much like the 2 loops up there, and consequently the dead code had been present in our code base for a long time, and it hadn't been found. So I was very happy with that one. Unused Fields is a global analysis plugin. I've been extending it lately to look for fields that are unused in the sense of they're not generating any useful work. So for example, an example up there, we've got a standard vector. We're pushing information into it, but other than that, we're doing nothing with it. My normal analyses don't find this, because we are in fact calling a non-const method on it. So we are actually modifying the object, but other than that, we're doing nothing useful to it. Surprisingly, there were quite a few incidents of this in our code base, which I suppose is not a surprise. When you've got 10 million lines of old code, you find a lot of stuff. So I started with this idea, and I extended it to a variety of other calls on various STL collection classes, and found us a bunch of dead code. SingleValue Fields is, I've extended that one as well to, it used to be only for fields that were declared on classes. Now it looks for any statically allocated values. It looks for kind of primitive type values, i.e. ints, char pointers, those sorts of things. It also looks for our string classes, and it looks for places where those things are only ever assigned a single value. So in which case it's not really mutable data. It can either be declared const typically, or it can be inlined into the relevant modules. Either way, I'm effectively extracting latent information and making it concrete. Int versus float was not my idea at all. A guy called Mike Oginski very interestingly pointed out that code where you are comparing an integer and a floating point value can never be true, and is generally indicative of somebody making a mistake. In this particular case, he found that mistake down in, I believe it was our drawing ML import code. So we then ran that using a Clang plugin. That was an interesting case. We wrote the plugin, and then we had to park it. It was using an API called evaluate as float inside Clang, and at the time, evaluate as float would throw its hands up in the air and crash on about half of the classes in LibreOffice. So we parked it, and 6 months later, I tried it again, and lo and behold, Clang was fixed. So that works quite nicely. Only found a few places, but it's nice to see that Clang is moving so fast. Unused enum constants. I initially wrote this to look for enum constants where you've got an enum, and one or more of the constants is not touched at all. That's a relatively straightforward case. So I cleaned out all of the dead cases where they made sense to do so. Again, there's an idea from Mike Oginski. And then we started looking for places where I had an idea in my head that there was a read-write analogy here. As in some cases you read information, in some cases you write information, and if you've got write-only information or read-only information, that's generally indicative of some kind of dead code. But it took quite a long time for me to find a mental model that I could use to analyze the AST. So in this context, write means we generate and store new information. So if you've got write-only code, you're storing an enum value into stuff, but you never ever look for it. Read means that we just check for the information, but we never store it. Now, as it turns out, write is better defined than read, which means I've actually managed to use the write analysis to find useful dead code. The read analysis, however, it largely spits out too many false positives, mostly because of things like casts, where you have an information, you load a file, and then you cast the data type in the file into an enum. So you're not really, the cast is acting as a write, which means you've got a read-write field, so it doesn't work very well. But the analysis produced nice stuff in the end. Redundant functional cast is is an extension of another plugin that where we're looking for normal redundant casts. In this case, we often had code that was accidentally constructing a new OU string from an existing OU string and then passing it into a method. And the method in this case was taking a const ref, so there was no point in doing that. So the plugin looks for cases like that. Collapsef was looking for odd code where we had two very small if conditions, and they could profitably be combined into a single if condition. I ran this myself, and it's not on by default because it's quite hard to find a balance, and I didn't want to annoy people. Static var looks for things that can be declared constant static, i.e. they can be, in which case they're stored in the read-only part of a segment when the code is compiled, and they can be usefully shared between different processes. Const field was a failure. It was a good idea. The idea was that we can declare fields const and thereby mark those fields as being effectively safe for multiple threads to access. However, when you mark fields as const, it tends to interact with other C++ features. For example, you end up with implicitly deleted copy and movement assignment operators, even though you have non-deleted copy and move constructors. So it tends to produce rather weird outcomes here and there in the code. So that one got abandoned, which is a bit of a pity. But you try some stuff, and sometimes things don't work out. Simplify construct was effectively a cut-down version of a Clang tidy check. There's already an existing Clang tidy check that does something quite similar, but it tends to be a lot more aggressive. So I implemented just the simplest case where we have things like unique Pitta and other things that take null pointer and don't need, they have default constructors already, so there's no need to do that. We have a class called OU stringbuffer, which is a mutable string class, internally manages memory dynamically. And as you can see, we were often calling the code, it's got an append method to add stuff to it, but if you're adding two strings together and then appending it to the string buffer, you're not really using the string buffer the way it's meant to be used. You're constructing an unnecessary temporary, so the plugin goes looking for places like that. And in fact, I think I did a rewriter here, so it automatically rewrote a bunch of that code. So we then don't bother, we don't need to construct the temporary anymore, so we're losing a bunch of temporary creations. Should return bool. Actually, we had a surprising number of methods floating around in writer, which appear to predate the presence of bool as a C++ data type. And consequently, those methods were returning int or long, and they were only ever returning 1 or 0, and they were being used as bool methods. So the plugin looked for methods that only ever returned the constants 1 or 0, and we converted those to return bool. So it's now more obvious what those methods are actually being used for. I then took my unused fields analysis, and I extended it to unused variables. So I looked for the similar kinds of things. In that case, we have a sequence, which is a collection class, and it contains strings, a string class, and we are modifying it, but other than that, we're not doing anything with it. So that's effectively dead code. So my unused variables more plugin goes looking for a bunch of patterns like that in our code and spits out complaints like that. Then we have a tools rectangle. We have a class in the tools namespace called rectangle and point and size. And those had methods that were returning non-const references, which makes the code a little bit awkward to read. It can be, particularly when we have code like that, you have a point.x, and then you're adding to it, which actually modifies the object, but it's not very obvious that you're modifying the object itself rather than modifying a temporary or anything. And particularly when it was buried inside other statements, it could be quite hard to read. So I wrote a plugin that not only finds these cases, it automatically rewrites them. So we ran that across the code base to make the code easier to read. Then I spotted an interesting error case where somebody passed a pointer into a parameter that was actually a Boolean, and C++ does a silent conversion for you. It does a pointer not equal to null conversion for you, and it was clearly not what was intended. The type system doesn't pick this up, so I wrote a plugin that goes looking for places where you are passing pointers and other similar auto-converted things into bool parameters, and it spits out a warning. Cellcall was an annotation we had that modifies the linkage. It modifies whether a method is internally linked into a library, whether it's externally visible, and we were using it in a lot of places that it didn't make sense. This was mostly leftover code, so we went through it and eliminated a bunch of it. And that is what I've been up to. Any questions? Yes?
You maintain another large C++ code base that goes back quite a while. How useful do you think your plugins are for non-LibreOffice based code bases?
The question is about using these plugins on other code bases. I think they'd be fine. They'd be a nice extension to the Clang tidy set of stuff. There's about 110 of them now. They'd probably need some tweaking to run on your code base, but I'm happy to help out if you want to ask me questions or do stuff. No. Yes, sir.
Can you go to slide 11 with the casted? My question is if the produced assembler code differs if you make this change.
No. C++ does short circuit evaluation.
Okay. Has somebody compiled LibreOffice with Clang and link time optimization?
Lubosh used to do that. Does he still do it? Anybody remember? We did do it. Somebody was doing it at one point. I'm not sure if they're still doing it.
So it's unclear.
Yeah.
Okay.
Yes, sir.
Have you upstreamed any of these checks to Clang type itself?
Miklos has upstreamed one of them, a macro check that he wrote. Other than that, no, I haven't upstreamed any of these. The ones that I'm most proud of are the ones that are least able to be upstreamed because they are.
Very specific.
Yeah. But there's. Sorry.
Still available open source somewhere.
Yes, they're part of the LibreOffice repository, so anybody's welcome to grab them. Yes, sir.
Where can we find these extensions or these?
They're all in. If you look in the LibreOffice Git tree, they're under compiler plugins. Somebody else? Yes, sir.
You also have plugins to get a code matrix.
Sorry?
You also get a code matrix, like a dependency or cyclic dependency detection or something like that.
No, I have not. Thank you very much.